everybody. So, my name is Andrei Petrescu. I lead the DevOps department at CloudHero. We're a DevOps and data consulting company. And today I want to talk about something that is very dear to my heart, and it's something that I've done lots of, which are migrations. Before I get into explaining the project that I want to talk about, on a show of hands, how many of you have migrated an application before? Okay. And how many of you think that migrations are easy? Nobody. Exactly what I thought. Actually, the last migration that I did was yesterday, and it was challenging. I'm not going to lie, it was challenging. But it was not challenging because of things that you would think of. Like when you think about migrations, when you think of challenges, you think of millions of users. You think of terabytes of data and so on. Those are challenges, but there can be other challenges. Like, for example, you depend on a third party to change the DNS records for you, and for 1 hour, you don't know what you're testing, if you're testing the old infra or the new infra. Maybe the things weren't tested enough. So there are lots of challenges that can appear which are not really technical. But in this talk, I'm going to go through some technical challenges and one business challenge. So first, to give a little bit of context. The migration that we did was for a customer of ours that we've had a long relationship with. And this was the initial infrastructure that we started with. At this point in time, this infrastructure was enough for their needs. So when we got into the discussions about the migration, it was because they had challenges and they needed a more scalable infrastructure. But just to set a little bit of context. So this customer at that time had 2 games. They had one game which was running on DigitalOcean and one game which was running on SoftLayer. The game was based on regular VMs. So there is a setup with a VM that had PHP-FPM. You had some nginx servers in the front that would proxy the requests, and they would be bootstrapped and created by Salt. So the setup was highly available. When they needed extra servers, we could create them because everything was automated with Salt. But there were certain things which, in that exact environment, couldn't really work because of how their application worked. For example, there was the dedicated cron VM. It was a VM which was running crons, which if it failed, well, your crons failed. They also weren't monitored. So if something failed, they would SSH into that VM. They would check the logs, and they would see if something went wrong. They also had dedicated VMs for queues, because they are processing messages when players are playing the game. They had a dedicated VM for WebSockets, for chatting in the game, which is also a single point of failure. They are very heavy on using MySQL, so they had a setup which has a MySQL primary and multi-secondary setup. It was a multi-secondary setup because they wanted to take as much load off the primary as possible. At some point in time, even before we did the migration, they started having issues with MySQL. It didn't matter how big they would make the MySQL server. It didn't matter how many secondary servers they would put into the MySQL cluster. It would still have issues. And this is a funny story because this was one thing that triggered the migration, but we managed to fix it before we even migrated. We are working with a colleague of ours, which is a MySQL consultant, and he did a very good job of changing their table structures and then changing their queries and so on. So we had something fixed even before we migrated anything. They have something very interesting, which is a manually sharded Redis. When you think of Redis, usually you think of a single Redis server, which maybe has some like the Sentinel and then secondary servers, or you think of an actual sharded Redis. Because at that time, for them, the overhead of managing an actual sharded Redis was too big, and a single Redis was not enough, they actually did something smart, which was they would write to 3 different Redis servers. They would basically hash some SQL queries, and then they would do a modulo, like mod 3 or something. And depending on what was the mathematical result, they would write to each of these sharded Redises and then get the result back. This work, we actually, at that time, we tried to migrate to DigitalOcean came up with managed Redis. the bad thing about DigitalOcean managed Redis is that it's mandatory that you use encryption. And if you ever used Redis with encryption, you may know that it kind of sucks. For high performance applications, you have a penalty in performance for every connection that you make to Redis. So it just didn't work. We tried to set up a sharded Redis cluster with a managed service with TLS, and it just failed. Like everything blew up the moment we tried to send traffic to it. So we went back to the regular Redis servers. The deployments, because the developers were comfortable with that, were actually done manually. So they would write code, and somebody from their laptop would SSH to all the servers, and they would just change the code. If you are familiar with PHP, it's not a compiled language, it's an interpreted language. So basically, you can just change the code, maybe clear the op cache, and after you do that, you just have the change file. So every time a new request comes in, it gives the new files. Something very dear to my heart, because I worked on that about 7 years ago, was the Grafana and Prometheus setup, which connected their 2 data centers. Basically, they didn't really have a monitoring setup at that time. And I worked to connect them with Grafana and Prometheus. I did the setup with a console that would automatically integrate with Prometheus, so that when new servers were spin up, they would get registered in Prometheus. Because otherwise, you would have to always change the configuration files, and whenever you create new servers with Salt, you have to add them to the configuration file, which is a hassle. Nobody wants to do that. And there was no logging stack. So that was the initial context. That's where we started from. Then they started having higher traffic, more users. They needed something more scalable. So we talked to them and say, hey, a very good idea is let's move everything to a more stable setup and a more mature cloud, which at the time and still is AWS, and to Kubernetes. But we had to start somewhere. So we just created the landings on AWS, and then we said, okay, first, we'll just take the game from software, which was like very low traffic. We'll take it, we'll put it on EC2s on AWS, just so you get comfortable at least with the console. We did that, we migrated. We actually managed to get lower costs from AWS. I know that might sound untrue, but it actually is true, because the servers from software were really bad. Like price performance was kind of sucked. Then, after we migrated that, okay, let's push the envelope a little bit. Let's create an Elasticsearch stack on AWS so that they can have some logging from DigitalOcean. So we created that as well. And then we started working on the migration to EKS for their high traffic game. But what do you think? There was a business challenge. The developers were not comfortable with Kubernetes. It was too big of a change for them. They didn't have experience with it. We did do a POC. They did look at it, and they said, nah, we're not going to go with it. So give us time. We'll just do other projects. Let's leave it like this. But a very interesting thing, and that's why I made that bold there, is when you're working in consultancy, I think it's very important to listen to your customers. Like, even if they say no when you started the project, listen to them, because they're your customers. If they're not comfortable with it, make them comfortable with it. Like, do as many POCs as it requires until they get comfortable with the setup, and then you can finish the migration. So we went a little bit further. Okay, we had the lower traffic game. We had that Elasticsearch cluster. They had a new game that they wanted to put out. Okay, let's put it on EC2s. Not Kubernetes, put it on EC2s, but still on AWS. It was okay, it worked very good. It even had an improvement. We managed to have managed services for database and cache. We used RDS and Elastic Cache, which was a big win compared to the other game, which had like self-managed Redis and databases. So we had to take it with baby steps. After we migrated, we put that new game in EC2. Chance was somebody joined their development team who we've worked with before and had experience with Kubernetes setups and migrations, because we did a migration with him before. So it was like a win-win situation. We worked very well, and after he joined, he took the initiative, and he was like, okay, I'm going to be responsible. I'm taking ownership of this. If something blows out, it's my fault. So we worked with him to migrate, but again, baby steps. We didn't migrate to AWS. First, we migrated to DigitalOcean Kubernetes service. Then after that, it was successful. Then we started to migrate to EKS. And after we managed to finish the migration and put it to EKS, they had another game which they developed that adopted Kubernetes from the start. So right now, every game that they create, they already have a platform that they can use to develop new games. But this was more of a high-level overview of the whole setup. Let's get into some challenges, some technical challenges that we had to overcome in order to finish this migration. The first two are, I wouldn't say big challenges, but they're things that do take time, and you must do them whenever you do a migration. You have to Dockerize all the components. And that means, okay, let me take the Jenkins configuration files. Let me build the PHP containers. Let me make sure that all the modules are there. Let me see what other components I have so that I can have everything running correctly like it is on the existing infrastructure. It does take some time. You have like lots of things to containerize. Then you have to build Helm charts if you use Helm, because you have to have a way to make that containers like package it somehow so that it's easy for them to run multiple environments and maybe even run new games whenever they want to build a new game. They don't want to go to the hassle of, they just want to write code. Aside from that, they want it to be deployed on Kubernetes. So that's what we worked on. We had that in mind when you started packaging it. Then these are the interesting challenges. Running cron jobs which need to run once per minute. They have cron jobs in their game, lots of cron jobs that run, they need to run exactly once per minute. If they run fewer than once per minute, if it takes like 90 seconds, players in the game are affected. And they see the latency. Aside from that, we had to implement the CI for the Docker images, which was like a whole different thing for them. Again, baby steps. Don't give them container the first time. Like, first, give them something, a CI tool. We gave them Jenkins because it's easier for developers to use. And then they would use Capistrano to deploy, not manually, but you couldn't give them containers from the start because they were not used to it. Another challenge was that they have a certain deployment method. I was talking about the fact that they would SSH into all the servers and then just sync at the same time. They have to do that. The way the game is made and the way they build certain features does not let you do a rolling update as you would do it normally in Kubernetes. If they would do that, they would have problems. So before even migrating, this was like a hard technical requirement. We have to do blue-green. If we cannot do blue-green deployments, it won't work. And lastly of all, there was some challenges relating to auto-scaling, because as I said, they didn't auto-scale before. We would create servers manually whenever they needed it. So the first challenge about running crons one per minute. You would say, hey, but Kubernetes supports cron jobs. Why didn't you use that? And I would agree with you. It supports running cron jobs once per minute, but it does not guarantee execution one per minute, because you have some overhead. Whenever that cron runs, it has to download the container. If the node does not have it, it needs to start up the container. The container needs starts to do something. It takes more than once per minute. Like it may take 90 seconds, not 60. And this was not working for them. We tested it, it didn't work. Also, they wanted to have logs for their crons, and they wanted to be alerted if the cron failed. You can do that with Kubernetes, but what I've learned in all these years is that developers love a UI. Like, they love a UI. Don't give them command line and tools which are hard to use. They love a UI. The solution, even if you might cringe a bit that it uses Jenkins, I'm not a really big fan of Jenkins, but for this it absolutely rocked for running the cron jobs. What we actually did was we had a Jenkins primary server, then we had some cron agents on the Kubernetes cluster, and they would be based on the actual code image. So it was like the code, it had the agent, and the primary was doing the scheduling. So whenever we had to run a cron, it would run on those agents immediately. It already had the code. We didn't need to wait for anything to spin up. So we had load balancing of the crons, no more single point of failure. They would have like 4 different nodes where they could run. We had logs because Jenkins offers you like logs for each run of your cron. Like you can go to a specific cron and then you can select, run 943. Let me look. You click on that and you already have the output logs that you can link to. You have fault tolerance, which kind of ties into the first one. You have agents which always run the latest version of the code. This is very important because even if it fixed that problem with running crons fast, you might also ask, like, why did you bother doing agents? Why didn't you just run like a single Jenkins server that had the code and then it run the crons? Well, because you'd have 2 different deployment methods. You would have to use containers for the cluster and like Capistrano for the Jenkins server, which you don't want to do that. Lots of things can go wrong. So we also had to have this thing of having uniform CI and CD for everything. So whenever they do a deployment, these agents are also deployed, not only their regular code. Also, we have hot starts. As I said, it's way faster to start running the cron. And you can just put in the Jenkins file, you can integrate it with PagerDuty. So whenever a cron fails, we are directly alerted via PagerDuty and we get an alert on the phone. Next challenge was regarding continuous integration, because you have to take them from manually deploying using SSH to take them into this world of containers. So first thing we did, as I said, we started using Jenkins and Capistrano, and then because they became familiar with that, we had to use the same approach, but instead of using Capistrano, we had to use Docker containers. The problem was that the agents kept disconnecting. We tried to debug this. We tried to put retry policies to try to reconnect to the Jenkins primary. It was a really flaky setup. Somehow these Docker agents kept disconnecting. To this day, I don't know why, the setup pissed me off so much that I didn't want to debug it anymore. So what did we do? Well, it should be somebody else's problem. I don't want to have that problem. I want GitHub to have that problem. So we just moved to GitHub Actions to their servers. So right now, they are responsible for running our builds. It improved reliability because they're managed by GitHub, not by us. But the technical challenge was moving so many Jenkins files to GitHub Actions. And again, you need to make sure that developers are comfortable with the whole process. And you have to plan it carefully. Because when we started doing it, we have 100 Jenkins files, let's move them to GitHub Actions. And then they would go and then they would click in GitHub Actions. And we would say, no, that is still in Jenkins. Or they would click in Jenkins, no, that we moved that. So they would get a little bit pissed off for that. So we had to have an Excel sheet where we would have all the jobs and a status of migrated or not migrated. So challenges, people challenges, and planning challenges as well, not only technical challenges. You have to keep people happy and keep them in the loop with everything that you're doing. Regarding deployment, as I said, the application did not support 2 versions running at the same time, so we had to use blue-green, and also we couldn't have downtime during deployments. So we couldn't have close all the pods and then just spin up new pods. It just didn't work. And also, even if they were doing the deployment so they usually have games somewhere during the day where the traffic increases by 10x. They should be able to do those deployments even in high traffic and not be affected by that. So what did we do? Well, we implemented GitOps with ArgoCD. The CD pipeline is triggered by GitHub Actions, and it actually has a script that does all of this magic. Basically, we have 2 colors. If you're not familiar with blue-green deployments, you have a blue color and a green color. One of these, at a certain point in time, holds the live traffic. So what would the script do? Well, it would look at these 2 colors, and it would see which one is live. Let's say blue is live. So they would say, OK, I'll update the image on the green one. I will look at how many pods the blue one has because it has traffic, upscale it, then use Istio virtual service to move all the traffic from 0 to 100% in that way, and then downscale the blue deployment because you don't want to waste money on servers that you don't use. And all of these steps are actually done in the script by doing commits to the Helm values file. So everything is kept as a commit log, and ArgoCD syncs these changes all the time until the deployment is finished. This is kind of how it looks like. I just talked about it. I won't go into much detail here. Auto-scaling, another interesting challenge. This is interesting because we've noticed that, I don't know if it is written to the game or to how PHP-FPM works in itself, CPU usage does not correlate with application performance. Like, you would think that your application performance will start to drop off when you reach like 100%, which is not the case. We saw that when it reaches 80%, then the response time increases, even if it's not 100%. So we had to do something about this, and also their new pods need to start up very fast. Because if they wanna, the auto-scaling usually is done when there are live games. So in that case, you can imagine people are entering the game, they start playing the game, the traffic is really spiky. So it starts increasing very fast. So what did we do? Well, to fix it temporarily, we just lowered the threshold. It might sound like a stupid solution, but it works. Just scale when CPU percent is 50%. We saw that 50% is the threshold at which response time is not affected. So we use that and then scale the deployment based off of that. Going forward, we are searching for a different metric to scale by. So maybe we'll look at PHP-FPM metrics, or maybe we can integrate it with New Relic because we already use that. For the part of starting new pods, we implemented AWS BottleRocket as the base OS for the worker nodes. If you're not familiar with BottleRocket, it is an OS that was created by AWS, which boots up way faster than a regular OS. So in this case, because the workers are spinning up fast, the pods are also spinning up fast. And also in the roadmap, in the following weeks, we plan on implementing Carpenter. We want to implement this because how auto-scaling works in the case of AWS, or in the case of everything, is that you have a feedback loop. So you just watch the usage over the last, let's say, 2-3 minutes. If you see an average that is over a threshold, then you start scaling, which takes time. Carpenter does not do that. It doesn't even use auto-scaling groups. It just sees, oh, I have pods impending, let me call the EC2 API and bring up new nodes. Again, cut out the middleman, just go straight to EC2. So it's way faster. Let's get to some actual migration challenges, because those were like pre-migration. That was, you had to fix that and have that sorted out before you do the migration. But when you start doing the actual migration, well, first of all, you have to solve the DNS latency problems. As most of you know, DNS does not propagate instantly. You can have a low TTL, but it's still not instant. There is a brief period of time where you're not certain if the records moved or not. So what we did was we actually moved the name servers to Cloudflare. And then for the first part of the migration, when we moved from regular servers to DigitalOcean Kubernetes, we used the load balancer, and we will switch like 5%, 10%, 15% until we knew that everything was working fine. But from the migration from DigitalOcean to AWS, we just had it proxied, and then we could change the record, and it was instant. Only problem was the WebSocket server could not be proxied because of the hard-coded timeouts. So for that, we had to pray that it worked okay. It did, so it's okay. Also, the database migration, this was very hard to do from DigitalOcean to AWS, because we said, we're migrating to AWS. Why not also migrate from MySQL 5.7 to 8? Why not in the same time? So we actually had a MySQL primary, which was 5.7. We had a MySQL secondary, which was an RDS, which was running MySQL 8. And for the life of us, we couldn't figure out why the IOPS usage of the disk was maxing out. For everything we were trying to do, it was maxing out. We did, after lots of troubleshooting, we saw that it was because of bin logging. Because the application uses MySQL so much, there are lots of events which get written to the bin log. And we tried, like, we went through the fastest disks that AWS has, like IO1 or IO2 with like 64,000 IOPS. And we actually pinpointed it down. In MySQL 8, there is a new parameter that gets introduced. It's called sync binlog, which actually, if you put it to 1, which is the default in RDS, it actually, for every binlog event, it flushes the disk. So that's something that was new in MySQL 8. We disabled that, so we didn't flush everything to disk. It is more unsafe, but it kept us sane, because we could finish the migration because of that. And also, there's a translation script that I won't go very much into detail because I have 5 more minutes. But also, this was a problem because we had to somehow make it work with containers. It couldn't be put into Git, and it somehow had to be put in containers. So we kind of did it with an init script that would download the file from S3 at startup. Some security improvements in the new setup. Well, as you may know, EKS has a strong authentication mechanism. Like, you first need an actual AWS account, and then you run into problems of being allowed using the EKS config map to authenticate there. So authenticate to the EKS is already, the security is baked in, and also it has a strong RBAC system. But aside from that, we say that it isn't enough. We also wanted to make it internal. So if you wanted to access the EKS IP, you had to connect through a VPN. So you have IAM protection plus network protection. And also, we have encrypted the translation script because it had some, because it has by default some sensitive data in the environment variables in Git. Here we try to use, we usually use Secrets Manager or SSM in projects. And it syncs automatically with Kubernetes. In this case, in their workflow, the developers found it hard to use Secrets Manager. They didn't like it. Also, not everyone had access to AWS, which does kind of make sense in a way. Like, you don't want to give everybody access, but in Git, everybody had access. So we just made that the source of truth. They push some environment variables. They are encrypted in Git, and then at the deployment time, it is being decrypted by ArgoCD. Other improvements. This is a really awesome one. It was not like this was more of an effort on the development side. We actually helped them with this, but this is something that they worked on. Actually, they worked on changing Redis to KeyDB. If you're familiar with Redis, it is single-threaded. So even if Redis stores things in memory, it does so one operation at a time. What KeyDB does is, I think it is still single-threaded, but the part of parsing the commands is multi-threaded. So instead of having 3 Redis servers, we actually only have like a cluster with 3 KeyDB nodes, but only one takes requests at a certain point in time. And they also had to build some a TCP proxy in front of it because HA proxy wouldn't work. So that was also a challenge on their side that they had to fix in order to make the application faster. And also, we helped them with building an analytics engine on top of Elasticsearch, because they also are very data-driven. So everything a user does in the game is logged into Elasticsearch, and then the marketing department uses that in order to make reports. Before, they were using like MySQL. They had a user which connected to a secondary, and they would get data. But with Elasticsearch, they managed to get even more data from that. Not only like how many matches a player, but now actually they see what a player does in the game. So they had to use Elasticsearch for that. So in closing, what were the benefits of migrating to Kubernetes? Well, increased reliability, no more single points of failure. AWS as well is a more stable cloud because it also benefits from multiple availability zones. Actually, for right now, we had the staging on DigitalOcean, and we are moving it to AWS, and we would see like frequently problems like DigitalOcean registry would fail, or some networking problem in DigitalOcean. These are way more frequent than AWS. AWS is more expensive, but it is because of something. You get something in return. Developer productivity, because now they can create how many environments they want. It's not like it takes 1 week to create an environment. You can just, if they want a new test environment to test a new feature of the game, it's way easier to do it now. Lower cost versus static servers, and here I don't want to say DigitalOcean versus AWS because that's not true. But if they were to have this set up on AWS as it was on DigitalOcean with servers with Salt that we would spin up only when needed, it would have been way more costly, because now we can scale down to like 3 servers during the when it's not peak hour. I wanted to say during the night, but it's a global game, so it doesn't really have a very, very low peak. Increase security, because now we can scan images. We don't need to patch machines. We need to update images. We can do faster updates because of this. We are basing ourselves on the fact that AWS updates their own image, and we'll always take the latest. We have intrusion detection configured with guard duty, and also we have IAM and RBAC. And we also have increased observability because Prometheus and Elasticsearch integrates natively with Kubernetes. Also, we have New Relic for APM. So in the end, a happier customer than they were before. And with that, that's my presentation. Thank you.